You know that device you're watching this on right now? It's kind of a modern miracle. Inside of it, there are literally billions of tiny switches, all working together in perfect harmony. But have you ever stopped to wonder how on earth we actually design something so impossibly complex? Well, that's exactly what we're going to dive into today.
And that's really the core question, isn't it? This question literally drives a multi-trillion-dollar industry. A modern smartphone isn't just one thing. It's a whole collection of dozens of incredibly complex systems, all crammed together on a tiny piece of silicon. The complexity is just mind-boggling. So where do engineers even begin to tackle a problem this big?
So you might be thinking, okay, there must be some single brilliant trick, right? Or maybe a team of super geniuses locked in a room. But the reality is actually so much more interesting than that. The entire chip design industry is built on a shared philosophy, a really clever way of thinking that helps tame all that complexity. And it all rests on three core pillars. Let's break these down real quick. First up, we've got design abstraction. This is the classic divide and conquer strategy. Instead of trying to solve one gigantic, scary problem, you just break it down into smaller, much more manageable pieces. Next, there's design automation. Look, humans simply cannot design something with a billion parts by hand. It's not possible. So we've built some incredibly smart software to do all the heavy lifting for us. And finally, we have design reuse, or what everyone in the industry calls IP. The idea here is super simple. If someone has already designed and perfected a component, you don't reinvent the wheel, you just reuse their work.
Okay, let's dive a little deeper into that first pillar, abstraction. Imagine you were trying to build a city, right? You wouldn't start by thinking about every single brick. That would be completely impossible. Instead, architects think in bigger terms, like buildings and streets and neighborhoods. Well, chip designers do the exact same thing. They don't worry about individual transistors. They use a much higher level language to describe what the chip is supposed to do.
All right, so first question in our little quiz for today, what is this language of chip design? You'll hear the term RTL thrown around constantly if you're in this world, but what does it actually stand for and what does it really mean?
RTL stands for Register Transfer Level, and this is a really crucial distinction to make. It is not a programming language like Python. A programming language gives a computer a list of instructions to follow, one after the other. A hardware description language, the kind used to write RTL, is fundamentally different. It's more like a blueprint. It describes the actual physical structure of the chip. You know, how data is going to flow between different storage areas, which are called registers, with every single tick of the clock.
Okay, so RTL gives us that high-level blueprint. It's great, but it's still a bit abstract, you know? What happens when we take that blueprint and we feed it into our fancy design software? What's the next level of detail look like? Well, that's where we get to something called GTL. And this is where that magic of automation really starts to kick in. There's a process called synthesis that takes our high-level RTL description and translates it or converts it into a gate-level netlist, or GTL. Think of it like this. If RTL is the architect's blueprint for the building, GTL is the super detailed construction plan. It specifies every single logic gate, those are the fundamental building blocks of the chip, and exactly how they're all wired together. Our abstract idea has now become a concrete, physical design.
Let's move on to our next pillar and see how this all builds up. Design reuse. You know, if writing your own RTL is like designing your own custom Lego brick from scratch, then using IP is like buying a pre-made Lego kit for a car or a spaceship. It saves an absolutely incredible amount of time.
But, you know, just like with Legos, these pre-made blocks come in different flavors. In the world of chips, you're mainly going to hear about two types, soft IP and hard IP. They serve a similar purpose, but they are fundamentally different in what you, the designer, actually get.
Soft IP is kind of like getting the instruction manual for a really cool Lego set. It's the RTL code itself. It's super flexible, you can adapt it, but you have to do the work of building it yourself. Hard IP, on the other hand, is like getting a pre-assembled Lego model delivered to your door. It's a fixed physical layout, so it's rigid, but it's been expertly tuned for the best possible performance. This is what's usually used for the really complex, really critical components, like the main processor core.
All right, so we've got our digital blueprint. It's a mix of our own custom designs and these awesome pre-built IP blocks. But how do we turn this file on a computer into something you can actually hold in your hand? Well, that's where the back-end flow comes in. It's like a digital assembly line.
This is where that second pillar, design automation, truly takes center stage. We're about to walk through a highly automated process that transforms our digital design into a physical layout that's ready to be manufactured. It's a pretty fascinating sequence of steps, actually.
So let's take a quick tour of this assembly line.
First up, we have logic synthesis, which we've already talked about. That's turning the RTL code into a GTL full of gates. Then comes placement, where our software meticulously, and I mean meticulously, arranges millions of tiny components on the chip. After that, we have clock tree synthesis. This is like building the chip's central nervous system, making sure every single part of the chip is perfectly synchronized. Next is routing, where the software literally draws the millions upon millions of tiny wires that connect everything together. And finally, we have sign-off, which is the super rigorous testing process to make absolutely sure our design is ready for the real world.
Now, you might be thinking that one giant company does all this, but the reality is that the chip design world is this vast, interconnected ecosystem. There are a ton of different players, and each one has a very specialized role to play.
A really great way to think about this is with an analogy. If designing a chip is like writing a book, then who is the author? Who provides the word processor? And who actually owns the printing press? Let's break down those roles.
So here are the three key players. First, you have the designer. Think Apple or NVIDIA or Qualcomm. They're the author. They come up with a grand vision and write the RTL. Then you have the foundry. This is a company like TSMC or Samsung. They're the printing press. They own the multi-billion-dollar factories, and they provide the super strict manufacturing rules. And finally, you have the EDA and IP vendors, companies like Synopsys or Cadence. They provide the word processor and the stock photos, the absolutely critical software tools and reusable IP blocks that make this whole process even possible.
Okay, now for a really critical question. You've completed your design, but you haven't actually made anything physical yet. And here's the kicker. Manufacturing a single test chip can cost millions of dollars, so you have to be incredibly sure it works before you press that big, expensive button. So how do you test drive a billion-transistor chip before it even exists?
Well, the solution is this amazing technology called hardware emulation. Essentially, you take your entire digital design and you run it on a specialized supercomputer that mimics the behavior of your final chip. This lets you test your design at incredibly high speeds. So fast, in fact, that you can actually boot up an entire operating system like Linux on your virtual chip. This is how you find and squash those critical bugs before you spend millions of dollars on manufacturing.
And just to put it all in perspective again, we're talking about designs with over 1 billion transistors. 1 billion. Every single one of those tiny switches has to go through this entire, complex process. It's just a huge testament to the power of those three pillars, abstraction, automation, and reuse, that we can manage this unbelievable complexity. So the next time you use your phone or your computer, take a moment to just appreciate the incredible ingenuity that went into its design. These principles of abstraction, automation, and reuse are truly the foundation of all modern technology. They're how we build the impossible. And it really makes you wonder, doesn't it? What impossible things are we going to build tomorrow?